So next speaker is Professor Gil-Ho from POSTECH Physics. His talk is entitled Engineering Graphene Josephson Junction for Sensitive Photon Detector. So yes, please, Professor Lee, please share. Yeah, we can see your slide and can you test your mask?
Yeah, can you hear me?
Yeah, okay,
great.
Please go ahead. Thank you. So we have 20 minutes, a little bit, we are behind the schedule. So,
all right.
So, thank you.
Yeah, this is Gil-Ho from POSTECH. Thank you for the kind invitation. So taking advantage of having Dr. Kim Chang-Fong as our previous speaker, let me continue to discuss about our effort on microwave detector. So this is done with great collaboration with Dr. Fong and Professor Kim and the Professor Dirk England and MIT. So as Casey Kim Chang-Fong already discussed about this IL range of single photon detector using the graphene Josephson junction, let us tune down the frequency of further and further lower range. So the entire Hertz range, if we have a single photon detector, then we may be able to investigate the origin of the universe by looking at the dark side of the galaxy, right? So when we tune down a little bit more, we reach the gigahertz range where most of the superconducting qubit operates. So when we have microwave single photon detector, we are able to detect the superconducting qubit much easier way. Currently, as far as I know, people have been using so-called dispersive measurement, where people inject a reference tone of the microwave nearby the qubit, and depending on the qubit state, this reference tone of the microwave will have some phase shift. So by measuring this reference signal at the room temperature again, and look for the shift of if there is any shift in the phase, we can infer the state of the qubit. So for that, we need to inject the microwave inside the fridge and get out the microwave out back to the room temperature by amplifying it. So that we need a lot of microwave lines and amplifiers, and it will be a lot of cost this overhead for measuring the qubit. But if we have microwave single photon detector, then we may be able to measure the qubit directly by counting the number of photon. If the number of photon is 1, it should be excited state. 0, it should be ground state. So also we can do some kind of remote entanglement based on this destructive measurement of the qubit. So the purpose of this work was to make the ultimate sensitivity of the Josephson microwave bolometer. So far, people have been using this thermal detector scheme where when the absorber absorbs the photons, this absorber will increase the heat, will increase the electron temperature or phonon temperature. So by increasing electron or phonon temperature, it will change some property of the material itself. Then by measuring the change of the material itself, we can infer if there were any photons or not. So for that, we need very, very small heat capacity of the material, such that even if we have very small energy input, we could anticipate very high change of the temperature. Then we will be able to measure some change of the system much easier. So smaller heat capacity is very important parameter that we are looking for. And that's why we use this graphene as a absorber. Because the graphene has linear band structure, when the Fermi level at the drop point, then basically electronic density of state vanishes. So that the electronic capacity also vanishes, almost vanishes. So we may be able to have very high sensitivity against the energy perturbation. So in fact, Dr. Fong in 2012 already measured the heat capacity of the monolayer graphene, and it was almost 100 times of Boltzmann constant per square micrometer square, which is very comparable to the fundamental unit. This is very small. And also the estimated temperature change when we have 26 gigahertz microwave single photon comes into 1 by 1 square meter, micrometer square of graphene, then we can expect about 100 or 200 millikelvin change in electron temperature. So then the question is, how can we measure the change of the electron temperature by 200 millikelvin within the thermal time constant is about nanosecond. So that's why we incorporate with the Josephson junction concept. So basically, Josephson junction is two superconductors are coupled through the non-superconducting material. So for this case, it's graphene. So when the superconductors are close enough and the graphene is conducting enough, then the supercurrent can flow by overlapping this superconducting macroscopic quantum phases. So when we bias the Josephson junction up to some certain current, which we call a switching current, the voltage will be zero because it will flow as a supercurrent. But above the IC, the critical current, the voltage will suddenly build up because the Josephson junction now cannot afford this input bias current flowing as a supercurrent. So this is basically Josephson junction and switching of the Josephson junction. So as already Casey kindly introduced, the strategy of our measurement is the following. So at the lowest temperature, the IC is something like here. And basically, this is the temperature dependence of the switching current. At the base temperature, we have about 1.2 microamp critical current. If we bias the junction with 1.1 microamp, which is smaller than the critical current, then the Josephson junction will stay as a zero voltage state. But if there is any photon comes in, then heat up the electron temperature from 200 millikelvin to the 400 millikelvin, the IC will suddenly drop below the 1.1 microamp. Then now the bias current is now above the critical current. Then the Josephson junction will switch some resistive state. Then we can detect the Josephson junction voltage. Okay, and the switching is very fast. It takes less than 10 picosecond. So similar. So for now, our task is we make a graphene Josephson junction and focus our input microwave into the graphene. So for that, we use this so-called cross-junction geometry. So this is the graphene, and this is superconductor. So these two superconductors form the graphene Josephson junction, and these two electrodes are basically microwave resonator that through which we inject our microwave. Okay. So when graphene absorb energy, it will increase the electron temperature, but it will lose its energy back to the bath eventually through multiple channels. So there are three channels we can think about. First is just radiation, black body radiation, but because we are at the millikelvin range, this can be almost negligible. And another is diffusion of this hot electron out to the electrodes. But remember that our electrodes are superconducting, and the superconductors are perfect thermal insulator. So that's why we can now ignore this, or we can think this diffusion cooling channel is almost vanishes in the Josephson junction structure. So only possible way for electron to lose their energy is through the electron-phonon coupling. So basically, energy transfers from electron to the phonon of the graphene, and this will be the dominant cooling channel. Okay, so this is our actual device. So a graphene Josephson junction is inside of this one, and this is basically half wavelengths resonator. So when we input the microwave in, this will make make this kind of current distribution. So the current fluctuation, oscillation amplitude is maximum at the center of this resonator, where we intentionally put our graphene at, so that the graphene will feel a lot of change of current, such that the ohmic dissipation happens the maximum. So that's how we couple our microwave into the graphene. So basically, this is the reflectometry, and when we sweep the frequency of the microwave, the reflection decreases down to minus 30 dB at the resonance frequency about 7.9 gigahertz that we intended. so from that, we can infer that about 99.9% of the microwave were absorbed by the graphene. And at the same time, the change of the supercurrent or switching current of the Josephson junction shows a clear dip. So that means the microwave is absorbed in the graphene, which caused the decrease of the supercurrent or switching current of the Josephson junction. So this is the proof of how our Josephson junction bolometer is working for now. Okay, so so this is switching current distribution. So when we have no microwave at the base temperature, this will have the highest supercurrent. So basically, supercurrent has some switching distribution. Okay, so when we keep the base temperature and shine the microwave, the IC decreases and changes the distribution, something like this. Whereas if we don't shine the microwave, but only increase the bath temperature, increasing the electron temperature by increasing the photon temperature up to 0.45 Kelvin, we can make current distribution almost identical. So that means the decrease of switching current by shining microwave is really due to the increase of the electron temperature, because the shape is almost identical. Okay, so by using the information of power dependence of the decrease of switching current and the temperature dependence of the switching current of Josephson junction, we can reconstruct the electron temperature of the graphene as a function of input microwave power. And this can be easily fit by this electron photon coupling, because now our situation is the following. We continuously input microwave into the graphene, and that power is continuously dissipated by electron photon coupling. And this equilibrium will make some electron temperature reach some equilibrium temperature. That is exactly what we are measuring for here. So by fitting this, we can infer the electron photon coupling sigma value, which is about this. But this electron photon coupling is like 100 times larger than the theoretical value. So because if you think the lower the electron photon coupling is, the more sensitive the bolometer would be, because energy doesn't dissipate fast. So that change of the electron temperature in equilibrium would be larger, right? So we want to know how to why this electron photon coupling is so big in the reality compared to the theoretical value to improve the sensitivity of the bolometer. So basically, we made a bolometer for the microwave using graphene Josephson junction. We want to calculate the figure of merit, so-called noise equivalent power. So this is basically the signal power that gives a signal to noise ratio of 1. So the minimum power that we can see any change can be defined as a power that gives the change of the switching current as much as the standard deviation of the switching current, right? So that is about 11.4 femtowatt. This is small value, but we have to consider the bandwidth of this detector, because this the whole process of the measurement of the change of the supercurrent will have some time constant, because if you think when we input the microwave, it will take some time for the resonator input coupling happen. Okay, that is about 1.6 nanosecond. And it will have some time for this energy to be dissipated in the graphene, which will take about 1.3 nanosecond. I will not discuss about how we estimate it. I will just skip this one. And there are another time constant. This is basically thermal time constant, which is how fast the electron temperature get back to the base temperature back. So the slowest process is about 1.6 nanosecond. So basically, within this 1.6 nanosecond, we would be able to tell if there is any power as much as 11.4 femtowatt. So the right way to say the figure of merit of this bolometer is to calculate this NEP, which is calculated this way, and is about 1 at watt per root hertz. Okay, right. So when we calculate this one, we then at that time we later realized that this is actually the fundamental limits of NEP of this graphene device. The reason is the following. The graphene size of our detector is about 1 micrometer square. This is very small size, such that electron temperature or even the temperature is not well defined, because the temperature is a concept for infinite size of the system, right? Thermodynamically, right? So there is some fundamental fluctuation of temperature itself, which is about this one. So because our heat capacity of the electron is very small, then the fluctuation of the temperature is about 1.1 Kelvin. This is comparable to the average temperature. So due to this fundamental fluctuation of this temperature, we will have some fundamental limit of NEP. And that is about this one, the yellow one, which is comparable to the value that we estimated from the experimental measurement. Okay, so then later we realize that, oh, we already reached the fundamental limit of the microwave bolometer. So then we can also think about, what if we make a single photon detector with making the measurement fast enough, right? Because the electron temperature decreased back to the best temperature within a few nanoseconds. We have to measure the change of the IC within a few nanoseconds, right, to resolve the single photon one by one. But let's just imagine that we can do that. Then we can infer the energy resolution we can expect by from the NEP that we measure. That is about 30 gigahertz. So still is larger than a few gigahertz where people usually do the superconducting qubit measurement, but by optimizing the temperature sensitivity of the Josephson junction and the minimizing the heat leakage to the phonon of the electron, and also developing fast enough measurement of the IC change, maybe we can shoot for the microwave single photon detector in the near future. So currently that work is done by collaboration with Dr. Kim Chang-fong and Professor Dirk England, funded by NRF AFOSL. Okay, thank you very much.
Okay, thank you, Professor Lee. We have one question already. This detector is assuming a thermal effect like a conventional TE sensor. Have you considered any non-equilibrium detection mechanism such as pair breaking, which occurs in Josephson detector too?
Okay, thank you very much. Yes, the thing is, the microwave energy is about micro EV, and the superconducting gap energy is order of milli EV. So the microwave single photons cannot break the Cooper pairs of the superconductor, even if it's aluminum. So yeah, we cannot expect the break of the Cooper pair using by this single photon detector. That's why we use the graphene as a thermal absorber. Yeah, but KC, Dr. Fong in the previous speaker discussed about the break of the Cooper pair of the superconductor by the IR photons, then where we demonstrate the IR single photon detector.
Okay, one more question. Could you summarize the absorption efficiency, which would be critical in total system detection efficiency? Yeah.
Yes. So this is bolometers. It's not a single photon detector, so that we cannot say the single photon efficiency. But what we can say is the absorption efficiency of the microwave into the graphene. That is about 99.9%. So that's absorption efficiency. And what we are measuring is the power of the microwave, not the photon number yet. So we want to make single photon detector in the near future based on our work. Thank you.
Okay, because of tight limitation again, we should move on. Thank you again for Professor Lee for the great talk.